Hello everybody, welcome to chapter 1.8. What we're going to talk about today are inverse functions. We're going to learn mainly how to do two things. Verify that one function is the inverse of another. We're going to do that a couple different ways. And then you can determine whether a function has an inverse function. So let's get started. Alright, so here's how we can begin. We're going to talk about what inverse functions are. It's important that you know that a function and its inverse, going to write in quotations here, undo each other. And it's also important to know that you can find inverses algebraically by replacing x and y and solving for y. Oh, I used the wrong word here. I meant switching. By switching x and y and solving for y. Excuse me. Alright, let's just get a little bit closer here. There we go, that's better. Alright, so let's do our first example. If we say we're asked to find the inverse of the function f of x equals x cubed. Remember that f of x here just means y. And so what we can do is rewrite this as y equals x cubed. We're going to follow our rule that says, that is not as focused as I'd like it to be. Let's try that. Okay. That says when we want to find the inverse, we switch x and y and we solve. So we're going to do just that. We're going to put y over here and put x over here. So we're going to say x equals y cubed. Now we solve for y. We're going to have to take the cube root of both sides, and we get y equals the cube root of x. And so what we can then say is that f to the negative 1 of x equals the cube root of x. It's important you understand that notation. F to the negative 1 is inverse notation. Alright, next example. Find the inverse of f of x equals x minus 5. Again, we switch out f of x and instead we put in y. We switched our x and our y, so we get x equals y minus 5. In order to solve this, you'd have to add 5 to both sides. So y equals x plus 5. Which means f to the negative 1 of x equals x plus 5. Okay. Let's write down a few other important notes about domain and range of inverse functions. It's important that we understand the domain of f of x is equal to the range of f to the negative 1 of x. The range of f of x is equal to the domain of its inverse, of f to the negative 1 of x. So all of their x values, all of their y values switch. That's what defines an inverse. It's also important that we understand functions and their inverses. reflect over the line y equals x. So for example, if I had the following graph, let's say that I had a line with the point 2, 0, and 0, negative 5, and I had a line going through this. Point here, and I had a line. And I drew my line all the way out. Okay. We'll call this one our f of x. Then what I know about this inverse is that it would have the point of 2, 0 with x and y switched. So it would have the point 0, 2. 0, and then, here, I guess I should have graphed that a little bit better. 1, 2, 3, 4, 5. 1, 2, 2, 0. And it would also, let's use a different color. It would have the point 2, 0, and it would have the point down here, I switched the x and y, I'd have the point negative 5, 0. So I'd go out 1, 2, 3, 4, 5. And I would connect those 2 points. Imagine your line's a little bit straighter than mine. I'm not the best here. Okay. And what we could call this line is f to the negative 1 of x. And what you can see they're doing, kind of roughly here, my sketch isn't the best, is they're reflecting each other over that line that goes perfectly diagonal through the coordinate plane. Right? This line is y equals x. And you can see our function and its inverse reflect over that line. Let's talk about verifying inverse functions. Verifying inverse functions. For example, we want to show that the functions f of x equals x squared plus 1, with x being greater than or equal to 0, and g of x equals radical x minus 1 are inverses. So what we can do is we can use composite functions like we just went over in the last chapter. We can use composite functions to sort of undo each function and then determine if the g of x is an inverse of f of x and so on. So here's how we start that. We take f of g of x, which means f of radical x minus 1. So I'm taking x squared plus 1, but instead of writing x, remember I'm using that x minus 1. So I say radical x minus 1 squared plus 1. I square radical, so the radical goes away. I get x minus 1 plus 1, and I get just x. If I were to do the opposite, if I were to take g of f of x, then I would get g of x squared plus 1, which means I would be squaring pardon me. I'd have everything under the radical still, but then instead of writing x, I would be writing x squared plus 1 And I'd still have the minus 1. So everything is the same except for the x. I wrote x squared plus 1. And what I can do here now is simplify this out to be the square root of x squared plus 1 minus 1. We can see that these two cancel each other out. I get the square root of x squared, or I get just x. And this is the nature of inverse functions right here. When we take the composite, we talk about f in terms of g of x, it gets x by itself. We talk about g in terms of f of x, it gets x completely by itself. Whenever that happens, when you take the composite function and you get x by itself, it proves that those two are inverses. Oh, need some more paper. Excuse me. Alright, let's show inverses another way. Let's show that fancy F and fancy G, I can't really do a fancy G, are inverse functions numerically. And what numerically means, you guys, is that it's involving coordinates, involving ordered pairs, inputs and outputs. So we can just say involving coordinates or tables of values. So we can first prove this numerically in a couple of ways. If we look at f of x, which is 3 minus 4x, and we look at g of x equals 3 minus x over 4, what we can do is, because we know that the domain of f of x should be the range of g of x, and that the g of x, or pardon me, the domain of, okay, I might have said this twice, but I'll say it again. The domain of f of x is the range of g of x, and the range of f of x is the domain of g of x. So, frankly, when we put in a point for f of x, we put in a value, we should get the opposite scenario when we plug into g of x. I'm going to stop talking, I'm just going to show you. Okay. So, let's find a point. If we were to take f of 1, we would have 3 minus 4 times 1, which would be negative 1. So, when we plug in 1, we get an output of negative 1. G of x, what I should get for negative 1, when I substitute in negative 1, I should get an output of 1. Let's see if we do. 3 minus negative 1 over 4. Well, 3 minus a negative 1, that's really 3 plus 1, which would be 4 over 4, which would be positive 1. So this checks out, and what we can conclude here is that f to the negative 1 of x equals g of x. G to the negative 1 of x equals f of x. Okay. Those two are inverses of each other. Another way to prove this, yet another way, is to look at a table. So, if we're asked to use a table of values to find f to the negative 1 of x, and we're given the following table, x, oh, not y, x and f of x, and we have the following 3 points. Say that we had negative 3, negative 2, negative 1, and f of x we got 10, 6, and 4. Well then, if I'm looking for f to the negative 1 of x, what should happen is all of my x's and my y's should switch. So, we can create this table by taking my x values from my first table and putting them in for my y's. -3, -2, -1. And my y values, my f of x values, would now be my x's. So I would get 10, 6, and 4. And this would be the answer to that question. Let's see. Existence of an inverse function. So let's talk about the horizontal line test. Existence of an inverse. All right. So we're going to be asked to use the graph to determine whether the function has an inverse. All right, so we talked about algebraically, we talked about numerically, now we're talking about graphically. So, if we have the following function, and I'm not sure, maybe if we just had, let's call this 3, let's call this 3. If we had a straight line, and that was our f of x, what we could do is we could perform the horizontal line test, which means we put a horizontal line through our function. And here, since it touches at exactly one place, we can say that an inverse exists. What we can do, we should also highlight down here too, what we're doing is the horizontal line test. I should have been more clear about that. Horizontal line test. Here's an example of the horizontal line test not passing. So say that we had the following function. If we had something like a cubic, maybe, let's call this -1, let's call this 1, let's call this 1. So what if our cubic did this? It went up a little bit past 1, went down, and then went back up. Cubics usually do that. If I threw a horizontal line through here, we can see, let's label this one, this is our f of x. Okay. We can see now that this touched at 1, at 2, at 3 places on our graph. So what we can conclude then is that no, this inverse does not exist. One last note on that, do not confuse the vertical line test and the horizontal line test. Vertical line tests are for determining if a function exists, if the relation is a function. Horizontal line tests are only for inverses, only to determine if an inverse exists. Okay, thanks for watching. We'll see you in class.